for the common emitter, we did on the example, okay, but unbypassed not yet. Okay, for the common collector and common base, we just derive, okay, the equivalent circuit, the input impedance, the output impedance, and also the voltage gain and current gain. Okay, we didn't even try the example yet. Okay, so today for first half of the class, I plan to discuss on the example, and then second hour of the class we will begin with the new topic. Okay, okay, so let's move forward, okay, to this one. Okay, I'm not going to explain again on the derivation. Okay, that one I have briefly explained and lecture, okay, in the previous class. So today, just on the so today just on the example, okay, the example. Okay, so let's begin. Let's begin on the draw a small signal AC equivalent circuit. Okay, assume this one you have submitted to the Padlet. Okay, so for the unbypass, okay, we have done this unbypass, okay, and also derive the circuit. Okay, here is the circuit derivation. Okay, I have done this with all of you. And then the unbypass means that the resistor here, there is no capacitor. Okay, so let's take a look on the example. I think some of you has tried the example. Very good, because what? Because I have explained the derivation, everything. Okay, so basically the example here is you repeating the same thing. Okay, so you repeat the same thing what has been lecture. So some of you has personal message me, and they have tried the example, which is very, very good. Okay. All right. Okay. So let me. So in this example too, so these figures actually shows the voltage divider circuit. Okay, so with no capacitor at resistor RE, so you have this one base, okay, collector and emitter. So at emitter there is no resistor, okay, sorry, at emitter there is no capacitor, okay, therefore it is unbypassed, okay. Common emitter unbypass RE. Okay, means that in your equivalent circuit, you need to include your RE. Okay, so let's draw the equivalent circuit. So all the capacitor will be short circuit. Okay, all capacitor will be short circuit. Okay, if I want to draw the equivalent circuit, let me copy a bit. Okay, so capacitor will be short circuit. Okay, short circuit. Okay, first things, okay, draw from base collector to emitter, from node to node. Okay, and you draw the equivalent circuit. Okay, the equivalent AC equivalent circuit will be like this. Okay, so you have resistor R pi. Okay, and then you have current source GMV pi. Okay, and then this is your base, collector, and emitter. Of course, at R pi you have V pi. Okay, so let's look at the emitter. So at emitter you have resistor RE. Okay, RE here is 1K ohm. Okay, and then you also have ground after RE. So this is all ground node. Okay, so at base node, okay, you have from the base here you have so voltage supply DC also grounded. Okay, And at base here, you have resistor R1 to the ground, okay, resistor R1 to the ground. And at base also, you have resistor R2 to the ground. Okay, therefore, here you have resistor R1 and R2 in parallel. Okay, 8.2K parallel with 1.5K. Okay, and then at the base, okay, you have capacitor C1 short circuit and you have RS, which is 600. Okay, and then you have VS, voltage source over here, and you have ground. Okay, all right, so where does the ZAC in being placed is here, okay, before the RS. So this is your ZAC in. Okay, now let's take a look on the collector part. So collector, you have RC. Okay, from collector, you have RC to the ground. Okay, you have RC to the ground, which is 4.3 kilo. Okay, and then after that at collector also you have capacitor out shorted and you have RL. Okay, RL here is 10K. Okay, and oops, right. So this is your V out. Okay, don't forget to put your V in. So this is your V in. Okay, and then Z out is before RL. So this is your Z out. So drawing this equivalent AC equivalent circuit will give you about 3 marks. Okay, with all the labeling. Okay, so full mark for this drawing. Okay, with all the
Madam,
hello, hello, yes.
no, just now your mic no clearly, but now it's okay.
All right, thank you. Okay, so drawing this equivalent circuit will give you 3 marks, if I'm not mistaken, 3 to 3.5 marks, okay, with all the complete labeling, okay, from node to node. Okay, to be safe is you need to put all the the node here, base, collector, emitter, and you go from point to point from this circuit, okay. All right, so let's calculate. Okay, so from the question, given the IC is equal to 0.37 milliamperes, so you are asked to find everything there. Okay, so in here, let's find the R pi first. Okay, the GMB phi and R pi. Okay, so what will be the R pi in this case? So R pi is equal to what? First, you need to calculate for the GM, okay, because given IC. So how do you calculate R pi? So what is R pi? R pi equal to?
Beta over GM.
Beta over GM.
Yes, beta over GM. So GM is equal to what?
IC over VT.
All right, IC over VT. In here, you will get IC is 2.37 milli. VT is fixed value. How much? 26 milli.
26 media.
All right. So GM equal to what? Can someone calculate for me?
91.2 milli.
91.2 millisiemens. Okay, Siemens. So beta over GM mean 120 over 91.2 milli. So this one would be, I think, 1.32K. Am I right? This one I have the calculation. Okay,
Yes,
so you
doctor.
need, yes, okay, thank you. So you need to find all these parameters first in order to move forward with your derivation, okay? So first thing is to find the ZAC in, okay? As ZAC in, so this is unbypassed. I'm not going to explain again what is unbypassed and everything. So you need to find, so ZAC in is equal to R1 parallel with R2 parallel with Z in B. So where is Z in B? So Z in B is here. Okay, so this is Z in B. Okay, so you need to find first what is Z in B. So Z in B is the from here to here, you have the total voltage over here, which is V total. Okay, so you have current here is IB. Okay, but current here, so as I have explained in the class, so this one is actually equal to the beta IB. Okay, and this is equal to the IE. Okay, so ZIB is equal to the is equal to the VT over IB. Okay, VT here is V pi plus VE. Okay, over IB. Okay, V pi here is IBR pi plus BE is IB beta plus 1 RE. And finally, you have the high B and you cancel out everything. So Z and B here, you will get the value is about 122.32 kilo ohm. Okay, so that is for the ZIB. Okay, for the Z out, okay, sorry, for the Z in, okay, therefore Z in is equal to the 8.2K parallel with 1.5K parallel with 122.32K. So you will get your Z in is equal to the 1.26 kilo ohm. All right. Okay, for the Z out, okay, Z out has been explained very detailed. Okay, Z out is where you have to apply the imaginary voltage over here. Okay, so these are the derivation. Okay, I don't want to explain further on the derivation. So finally, Z out is equal to the you apply V test and I test, and then you get the Z test. Okay, so finally your Z out is equal to the Z test parallel with IC, and it is approximately equal to the RC. Okay, so therefore Z out is approximately equal to the RC. Okay, you have to look again on the derivation and everything. I'm not going to touch it again today. So 4.3 kilo ohm. All right, so this is for the Z in and Z out. Okay, so next is on the AV and AVOC and so on. So they ask you to find the so Z out done. Okay. Okay. So Z out done. So now AVOC. AVOC is V out over V in without RL. Okay. So AVOC is actually equal to V out over V in without RL. Okay. So V out. Okay. V out is equal to the voltage across this resistor, but without RL, meaning that V out without this 10K. Okay, so V out without 10K is equal to what? Current times resistor, right? So resistor involved only 4.3K. So what will be the current here? What is the current over here?
Negative GMV pi.
Yes, negative GM V pi. Okay, negative GMV pi. All right, so in this thing, okay, in here, so you have V out negative GMV pi times only RC because this is AVOC. So V in here, it is actually from this node, okay, to the ground. So it is actually equal to the VT over here. Okay, VT over here. All right, so it is equal to the to the V pi plus VE. Okay, V pi plus VE, which is this one. So this one, okay, this one. So V pi plus VE is equal to this portion, everything. Okay, everything here. So just put everything, the value there. Okay. Okay, in here, it is equal to the V pi plus VE. Therefore, I want to simplify this. So V pi is equal to the IBR pi, RC. Okay, and then this is IBR pi plus beta plus 1 IBRE. Okay, so I moving from here, cancel out everything here. So finally, from the derivation, you simplify this. Okay, you simplify blah, blah, blah. Okay, whatever here. So you will get negative GM 1 plus GM RE. Okay, so where are the derivation? I have actually derived everything here. So for the AVOC, how we managed to get this? Okay, you better see on your own because we replace R pi with beta over GM. Okay, all right. So finally, you will get this. Okay, and then if you calculate, put all the value, GM you already calculate here, which is equal to 91.2. So negative 91.2 milli. Okay, times RC is 4.09K over 1 plus 91.2 milli times RE is 1K. Okay, therefore this one you will get 4.25. Okay, 4.25. Okay, so now we finish the part AVOC. Okay, we're going to repeat again for the AV with RL. So why not I put it side by side so you will be much clearer. So we V in VI with RL now. Okay, so in here, if it is with RL, therefore the V out is actually you consider both resistor in parallel, which is the RC and RL. Okay, what are the current flows? Of course, the same current, which is negative GM V pi. Okay, so it will be negative GM V pi times RC parallel with RL over V in, which is the same thing, V in, same portion, okay, which is plus VE, the same thing, okay. So if you summarize this, so negative GM, IBR pi, and this is RC parallel with RL over IBR pi plus IB beta plus 1 RE in this case, right? So you will get over here, everything here, it is actually equals to negative GM, okay, RC over RC parallel with RL over 1 plus GM RE. So here you will get negative 2, you plug in all the values over there. Okay, so you will get negative 2.97, negative 2.97. Okay, so that's how you do it. If you want to do the AVOC one, okay, like this one also can. So you find the AV and this is AVOC, and then how you find AV is the same thing. Okay, so if you want to apply this box model also can, same, doesn't matter. Or if you want straight away V out over V in like this also can. Okay, you will get the same answer, definitely. Okay, now you have the AV. Okay, what is AVS? Okay, AVS, you might need another one. Yeah, so AVS is equal to, AVS is equal to the V out over Vs. Okay, means that this is the voltage gain referring to the source. Okay, referring to the source. Okay, to the voltage source. Okay, to this source. Okay, and then what is this? So you need to simplify. Okay, it is each actually equal to the V out over V in over Vs. Okay, it's like you canceled it out, but it is actually not. Okay, so where does you get this portion? It's from the input circuit here. Okay, from the input over here. So it is actually from here, okay, V in over Vs. You need to do the voltage divider to find V in, okay. So you will get this one, okay. If you do like this, so this is your Vs, and the transistor model here is Rs, and then you have here your Z in, okay. So this is your V in. Okay, how do you find V in? You need to apply the voltage divider. So V in over Vs, it is actually equal to the Z in over Z in plus Rs. Okay, from here, V out over V in. So this portion you already calculate, which is the AV just now. And this portion, it is actually equal to Z in over Z in plus Rs. Okay, AV just now, you get negative 2.97. Okay, your Z in is 1.26K. Is it right? Okay. What was your Z in just now? Am I correct? The Z, oh yeah, 1.26K, betul. Okay, so 1.26K plus Rs. Rs is given 600. Okay, finally AVS is negative 2.1. Okay, negative 2.01. Okay, so this is for the AVS, quite long, everything are asking here, okay? And then for the AI and AIS, okay? So for the AI, of course, you can do the equivalent circuit, or you can actually do one by one if you want to do. So this derivation, actually I find I out from the transistor model circuit. Okay, you find because we already have the AVOC, then you need to find the I out from the AVOC circuit. Okay, you can also do like this. Okay, the same thing. Okay, same thing. Okay, that's why some of you has tried the example 2 and you got correct answer. Okay. Okay. So for the AI, okay, for the AI, okay, for the I out is equal to the so in this case AI, so I out, it is equal to the AVOC V in, okay, over Z out, Z out plus RL. Okay, I'm not going to draw it again. It is the same thing like has been derived previously. Okay, so this AVOC is equal to the I in Z in. Okay, and then this is Z out plus RL. And finally, okay, your I out over I in, which is represent as AI, is equal to the AVOC Z in over Z out plus RL. Okay, all the values here, you already have all the values. So negative 4 AVOC just now, how much? 4.25. Okay. Okay, times Z in 1.26K over Z out equal to RC 4.3K plus RL is 10K equal to the negative 0.37. All right. Okay. Okay. So for the AIS, okay, the same thing. So it is I out over IS. It is same like I out over I in times I in over IS. So it's like you cancel out, but you not actually. So the AIS, it is equal to the AI you have calculated before, and I in over IS. Okay, I in over IS, it is actually the derivation from the input loop here where you transform the voltage just now. You have VS, okay, in series with RS. Now you do the voltage to current transformation. You have now current source in parallel with RS, then you do circuit divider rule. Okay, you get the portion for IS, I in over IS is equal to the RS over RS plus Z in. Okay, same thing here. So this is equal to the AI times RS plus Z in. Okay, so here you will get about plug in all the value. This is 0.37 and RS is 600. So 600 plus 1.26K. So you will get here negative 0.12. Okay, for the voltage gain, current gain, and everything, this is unitless. Okay, unitless. Okay, so no unit. So you have done these two. So AP is equal to the AI times AV. Okay, so if you want to check the answer, okay, you can actually check here. So we have all the solution here, but still this solution, they didn't derive everything, so they have the correct answer. Okay, so but I derive it for you, at least a bit of the derivation there. Okay, some sort of a recall. Okay, and that's it for the common emitter unbypassed. Okay, so this one is done. Okay, next is the common collector. So this common collector, we have derived it. Okay, I have for those who missed the class, okay, definitely you're gonna be blurred if you didn't watch the recorded video for the past class. Okay, so I'm not going to explain again. Okay, for those who missed the class, but so this is for the common collector. So common collector means that the collector has no resistor and it is straight away to the voltage. Okay, when you convert it into the AC equivalent circuit, then you have to short your capacitor and this voltage become grounded, and therefore collector will straight go to the ground. Okay, the collector will go to the ground. Okay, this is how it looks like, the circuit, the AC equivalent circuit for the common collector. Okay, and then the rest of the node of the base and emitter are the same. What are the same thing again is the block, the red shaded area here, which is the hybrid pi model. This is also the same. Okay, we have R pi, GMV pi. Okay, and at emitter you have resistor RE, and emitter you have R pi and RB. Okay, so let's take a look on the example here. So this example 3. So as you can see, some of your friend also has tried. It is actually the same circuit like this one. Okay, exactly same circuit actually, with okay, the same circuit where collector go to the ground. Okay, all right. So let's take a look here. Okay, so you have given everything where the IC also given. Therefore, here we know that you have to calculate first, since it has the same value. Okay, just now, so you need to calculate. So the GM is equal to the IC over VT. Okay, same value like in the previous one. Therefore, same answer, I guess. Okay, milli over 26 milli. Therefore, here you have 91.15 millisiemens. Thank you. And the R pi is equal to the beta over GM. Here you will get 120 over 91.15 milli. Here you get 1.32 k ohm. Okay, so let's do the AC equivalent circuit. So there is a little bit different actually. So in the previous derivation, we don't have this resistor, but we can go from circuit to circuit, from circuit to circuit, from node to node. Okay, oops, I need to copy. Right. Okay, so to draw the AC equivalent circuit, okay, to draw the AC equivalent circuit, okay, you need to short circuit the capacitor. Okay, short circuit all the capacitor, and this DC voltage become grounded. Okay, then we will draw from node to node. Okay, so the first thing, the main thing is you have to draw the hybrid pi model. So you have R pi. Okay, so this node is base. Okay, and then this is your ammeter. So and this is your GM V pi. Okay, this is collector node. All right, so at ammeter, you have resistor ammeter over there. Okay, at ammeter, let's solve for the ammeter first. You have RE, okay, to the ground. Okay, and then collector will go straight to the ground. Okay, so collector will go straight to the ground. Okay, I want to draw it in the same node. Okay, because it is straight to the ground. Okay, and then at ammeter over here, ammeter. Okay, you have capacitor short and go to RL. Now your output is at ammeter. Okay, output is at ammeter. So this is your RL. All right, so this is your V out. Okay, look carefully, the Z out is before RL, therefore this is your Z out. Okay, now let's move forward on the base. Okay, base node, you have resistor R1 and resistor R2. Okay, resistor R1 to the ground, resistor R2 also to the ground. Therefore, at this node, you have two resistors in parallel to the ground, which is R1 parallel with R2. Okay, and then at base also you have resistor RS. This is short circuit, and then you have resistor RS. Okay, to voltage here VS, and to the ground. All right. Okay, so where is your Z in? So Z in is V4RN. So this is your Z in. Okay, so you have Z out and you have Z in over there, and put everything here your V in. So this is your V in. Okay, V out already put there. What else? That's it. So these are all the correct notation, everything. So you definitely you will be asked to draw the AC equivalent circuit. So when you draw the AC equivalent circuit with the proper labeling, everything with the Z in and Z out, you will get full mark. Okay, full mark for this. Okay. All right. So in here, if you still remember, okay, you have the at this node, okay, so Z in, it is actually equal to the R1 parallel with R2 and parallel with some other resistor over here, which is represent as, so you have V total over here. Okay, the same concept like in reverse in the unbypassed just now. So you have here is Z in. Okay, Z in. So you have to parallel everything. So for the Z in, it is actually the same derivation as in the unbypassed just now. So I go back to the unbypassed just now. So how did you derive the Z in B? It is actually you calculate the total voltage here, the derivation for total voltage over current IB, this one. Okay, the same thing happens here at the common collector. So I have also derived it here. So Z in over here, it is equal to the V total over IB. Okay, the same thing. Exactly same thing. Okay, exactly the same. So Z in B. All right, so Z in B, where should I write the Z in B? So Z in B, what is the proper way to write? So Z in B is equal to, after the derivation, it is actually R pi. Okay, so let's do one more time. Okay, so Z in B, it is equal to the V total, which is V pi plus the VE over here. Okay, VE over IB. Okay, we know that, okay, V pi is IB R pi. Okay, but VE equal to, oh, sorry. Wait. Okay, VE is equal to IB beta plus 1. Okay, because this is IE. What are the total resistor at VE over there? What are the total resistor there? Is it just RE or RE parallel with RL?
RE parallel RL.
Yes, correct. Okay, it is RE parallel with RL. Total voltage over here. Okay, total voltage over here at the VE. So VE actually equal to V what? Equal to V out. Okay, is this the same thing? Yes, yes, correct. Okay, so over IB. So cancel out B. So you will get your Z in B there. That Z in B is equal to the R pi plus beta plus 1 RE parallel with RL. Okay, that's how you get your Z in B. Okay, in this derivation, okay, in the circuit derivation here, didn't have RL over there. Therefore, for the Z in B, just up to RE. Okay, no RL. But if you have RL, then you have to parallel with RL. Are you all clear with that? Very much.
Yes, yes.
Yes,
All right.
doctor.
All right. Okay. Thank you. Okay. All right. So you parallel everything there. So R1. So R1 parallel with R2, parallel with Z in B. So you should get this one. Can someone calculate Z in B for me? How much is the Z in B over here? Doesn't matter. I have the answer. So if you calculate the Z in B here, where to put? Where to put? So Z in B is equal to the 112. No, 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 no. 111.32 kilo ohm. Okay, so Z in, okay, you parallel everything. R1 8.2K, parallel with 1.5K, parallel with 111.32K. So finally, Z in, you get here about 1.25 kilo ohm. Okay, all right. Right, that's it. Okay, so for the Z out, okay, for the Z out, as you can see here, you have here Z out is here. Okay, to solve for the Z out, okay, it is actually you have to inject the voltage. Okay, you inject V test, you detach RE, and then you inject V test, which is imaginary voltage. Okay, and then you get the Z test. So finally, Z test is equal to the V test over I test, which is equal to the RB plus R pi over beta plus 1. All right, but this RB is just this RB. Okay, this RB. Okay, but in your case, your RB will be who? Will be all these things. Okay, R1 parallel with R2. Okay, so therefore you will get your Z test. Okay, Z test. So Z test here is equal to the RB plus R pi over beta plus 1. So here are the derivation. Okay, I'm not going to do it again, but in here, your Z test is equal to, wait. So actually, Z out is equal to the Z test, okay, parallel with RE. Okay, see, Z out is before RL. Okay, Z out is before RL here. This is RL, this is Z out. Therefore, Z out does not include RL. Okay, usually like most of the time student get confused or nervous or panic, so they include the RL, they parallel all. No, it's wrong. Okay, see where the Z output being is placed is before RL. Therefore you see at all voltage seeing from this node to here. Okay, so you need to inject voltage. In this case, Z test parallel with RE. So in this case, okay, you have your Z test, which is RB plus R pi just now over beta plus 1. But your RB here, okay, in this case, you have these two resistor, R1 parallel with R2, okay, R1 parallel with R2. Therefore, your RB here is equal to the R1 parallel with R2 plus R pi over beta plus 1. So this one, you will get, sorry, not only R1 parallel with R2. So what are other resistor here? Okay, so in order to do the Z test, okay, Z test, okay, for the Z test, so you have to, sorry, okay, so you have, in this case, only RB, okay, because this is the circuit, okay, only RB, at the base, only RB, okay, and you have no voltage source over here, okay, so if you have for this case, when you inject imaginary voltage over here, so this voltage source is shorted because we just want to use the V test, okay, the imaginary voltage. So this will be shorted. Therefore, your Z test will include when this short. Therefore, you have all three resistor, RS parallel with R1, parallel with R2. Okay, so this one you have another portion here which is RS plus R pi. Okay, the same derivation for V test I test, but then with all the resistor at the base, okay, including the RS. So in this case, it is 8.2K parallel with 1.5K, parallel with 600, and then the R pi is 1.32K over beta plus 1, 1 to 1. Therefore, you get here Z test, I don't know what is the value. It is in ohm. And finally, you get this Z test, okay, parallel with your RE, which is 1K. Okay, so your Z out is so RE, Z test parallel with RE over here. So this one. Okay, can someone calculate Z test for me? How much is the value here? For those who has tried, or you straight away, or you stuck for the Z test. So this is how we get the Z test. Can someone calculate for me the Z test, please?
Fourteen point three.
14.3.
Yeah.
3.
Yeah.
All right, thank you. Okay, so 14.3 parallel with 1K here, you will get 14.07 ohm. I only have the final answer. Okay, so that is for the Z out. Okay, for the Z out. All right, so next we have done on the Z in and Z out. Okay, so Z in and Z out. Okay, I want to skip the AVOC. Can you do it on your own? So let's straight away do the AV. Okay, you can do on your own and you find the value over here. Okay, but I want to do for the AV. Okay, AV with simplification method. Okay, so we know that our AV, okay, AV is equal to the without RL, okay, with RL, sorry, with RL. Okay, so in this case, your AV is equal to the negative GMV pi times all the resistor, everything there. Okay, all right. Okay, so I think we may try. It's okay. I find the AVOC. Okay, is equal to the V out over V in without RL. Okay, without RL. So this one, so V out is equal to what? Just now I told you V out equal to what?
VE.
Correct, VE. Okay, VE is equal to IB beta plus 1 RE parallel. In this case, with the RL, therefore you don't have to put your RL. Okay, and then for the V in, okay, I think it's okay. I just straight away usually won't be asked you about the VOC. Okay, you can straight away do. Okay, so in this case, V out equal to the VE. Okay, VE is current here. Okay, current here beta plus 1 and everything there. Therefore, I can say that it is equal to the this portion. Same thing here, over here. So it's equal to the what was it just now? IB beta plus 1 RE parallel with RL. Okay, IB beta plus 1. Okay, now it is with RL, therefore RE parallel with RL. Okay, and then V in. Okay, V in is equal to, what is V in? Student, what is V in?
VT.
Yes, it is
V pi.
equal to the not V pi, it is V, it is V total here, V total. Okay, therefore V pi plus VE. Okay, which one? All the thing over here. Okay, all thing here. Okay, so V in is equal to the V pi plus VE, which is IBR pi plus beta plus 1 IB, and in this case RE parallel with RL. Okay, so cancel out all this thing here. So you're gonna have this one, it is beta plus 1 RE parallel with RL over R pi A beta plus 1 RE parallel with RL. Okay, so this is gonna be your AV. Okay, AV. Okay, so if you calculate this, okay, for the common collector, okay, it is has to, for the characteristic is the AV must be equivalent to 1. Okay, if you get the value of your AV here not equivalent to 1, means that you are calculated wrongly. Okay, in this case, okay, you will get the correct answer. Okay, you will get the correct answer. Therefore, it is equal to the about 0.989. Okay. Okay, other than that, I just want to show you there is other ways to find AV. Okay, so AV is equal to the V out over V in. Okay, V out from here, we know that if we want to make this term in term of GMV pi, okay, so the current flowing through here, so V out is resistor, these two resistor in total. So can I take current GMV pi? Is this the same thing, right? Because of what? GMV pi is also equivalent to the beta IB. Okay, so you know that IB is approximately, this is IC. Okay, IC, current at IC. So beta IB, it is approximately equal to the IE lah. So because IE approximately equal to the IC. Okay, so if I want to make it like the current just straight away here GMV pi, okay, the resistor here RE parallel with RL also can. This is not wrong. This is the same thing. Okay, and then the V in, I want to take V pi. Okay, V pi. Okay, I want to take V in. This V in is V total, but I want to take V pi plus this V out voltage, which is the same thing just now on top, which is GMV pi times with RE parallel with RL. It's the same thing. So in here, so you're gonna have here, this is equal, so V in here is equal to the V pi plus VE or V out. Therefore, V pi here and V out is the same thing as the bottom one over here, which is GMV pi times RE parallel with RL. Okay, the same thing. You can cancel out the GM. Here you will get GM RE parallel with RL over 1 plus GM RE parallel with RL. Okay, if you do the calculation, you will get almost the same answer, 0.9 something. Okay, are you all clear? So you choose whichever you prefer. This way also correct, this way also correct. Are you all clear? Hello?
Yes, doctor.
Yes, Doctor.
Yes, great. Okay. Okay, so for the rest here, so AVS, AI, AIS, everything here you can do on your own. Okay, so but now I want to see a little bit on the AI. Okay, for the I out and I in. So I think it's the same thing I have derived here. Can I trust you that you do it yourself? Okay, to find the AI and everything here, same thing over here. Okay. Okay, but because I want to move forward on the common base, okay, I did notice that it's almost 1 hour. So let's try on the common base. So common base, okay, has been derived for all of you here. So the common base means that, oh, I need to recall again. Okay. Okay, sorry. So for common emitter, okay, common emitter. Where is the circuit? All right, doesn't matter. Look at here. So for the common emitter, so this is your circuit. So common emitter is grounded. Okay, emitter is grounded. So what are the input here? Input is base. Output is at collector. So output connect to collector and emitter grounded. While for the common collector, this one common collector, in this case common collector is grounded. This is your C, collector is grounded. Where is your input? Your input again at the base. So this is input at the base. Your output now is at emitter. So this is for the case of common collector. For the common base, okay, okay, your base is now grounded, okay, and then you have your input at emitter, okay, and output at collector. So different, okay, very different from the other derivation, okay, but the calculation for me, common base is the simplest one, okay. So this is the derivation for the common base. Okay, this is the circuit where you draw from node to node and everything. I have derived very detailed, okay, in the past class. Okay, let's take a look on the example. Okay, so this is the example. As you can see, you have the collector and everything here. So this is base, okay, collector and emitter. May I know, is this NPN or PNP?
NP.
Yes, this is NPN, okay, not PNP. Why? Because the current from base to emitter here is going out, okay. It is like this actually, okay, like this. So this is your collector, emitter, and base. So when current going out from the base to emitter, this is NPN, okay. All right, so let's derive on the AC equivalent circuit. Okay, so let me copy. Okay, so this actually this is from past year question, not past year, good test, if not mistaken, but past test lah, if I'm not mistaken. So looks like complicated. Oh, they got here and there all the cabang-cabang one got the R2 here, R1 there. So looks so complicated. Okay, now let's derive together the AC equivalent circuit. Okay. Okay, AC equivalent circuit. So what happened to all capacitor is shorted, capacitor shorted. Okay, all the capacitor shorted. All right. Okay, and then the voltage are all grounded. Okay, voltage grounded. Okay. All right, so let's draw. So you have here, do not forget to draw everything, the box, okay, the box here, which is include the GMV pi and the R pi, okay, the hybrid pi model. Okay, in this case, so this is PNP, therefore the current is to the left, okay, to the left from emitter to collector, but in our case, it is from collector to emitter because this is NPN, so current is going down. Okay, for the PNP, current is going up. Okay, in this case, current going up. Okay, current going up. Okay, from emitter to collector. That's why the current, the GMV pi here is to the right. Okay, from emitter to collector. Okay, so let's draw the circuit over here. So AC equivalent circuit, of course, you have to draw, where should I start? A little bit here. Okay, so this is your R pi. Okay, and this is your emitter. Okay, across this you have your GMV pi. Okay, so GMV pi is same like the current for current IC. Okay, in this case IC is going, so this is your NPN. Okay, NPN. Okay, so this is collector, this is emitter. Okay, this is base. So current going into emitter, this is NPN, and current going down, okay, for the IC. Therefore, current here to the left because from collector to emitter. Okay, GM V pi. Okay, put everything here. All right, sorry. So this is base over here. So GM V pi must be VBE. Okay, VBE. This is the V pi. Plus is at base. Therefore, plus is here. Negative is here. Okay. Do not wrongly put the label. Okay. Every time you have to refer. So V pi is actually equivalent to the VBE in the DC analysis circuit. So when plus is at base, therefore in this case, plus also at base. Okay, so GMV pi is equivalent to the IC. Okay, in this case, if your IC is going down because NPN going down, therefore going down means from collector to emitter. Therefore, your current source GMV pi here is also, it is equivalent to the GMV pi in this case. Okay, therefore your GMV pi current source here must go from collector to emitter. All right. Okay, let's go straight. Okay, so at the base, so let's settle at the base. Okay, what happened? So this capacitor short, this is grounded. So what happened to the R2? Again,
Short circuit.
short circuit, correct. Okay, R2 short circuit. Okay, what happened to the R1? So from this node, okay, to the ground, okay, and from this node to the ground also. What happened to the R1?
Also short circuit.
Also short circuit.
Also
Okay,
short circuit.
correct, correct. So also short circuit. Therefore, at base here, there is no resistor RB. It is go straight to the ground. Okay, just like that. Okay, and then let's draw at the emitter. Okay, base, collector. Okay, that's why this is a past test question. So it is quite tricky over there. Okay, some student put the resistor, but then all the resistor at the base are short circuit. Okay. All right. So at emitter, what do you have? You have resistor RE. Okay, RE to the ground. Okay, you have RE over there, and then you have collector, collector, capacitor C1 short, okay, and then you have RS, okay, and then you have VS over here, okay, VS. All right, Okay, so in here, do not forget to put your V in. So this is your V in. Okay, Z in is before RS, so this is your Z in. Okay, what else? Nothing else. So let's draw at the collector. So at collector, you have RC to the ground. Okay, RC to the ground. So you have RC to the ground. Okay, but not finished yet. Okay, because at this collector also you have capacitor C2 to this to short circuit, and you have RL. So you have another one resistor here, RL to the ground. Okay, put your V out over here. Okay, and then Z out before RL. Okay, that's it. Okay, that's it. Okay, so in this case, okay, being explained that this is involved with two nodes over here. Therefore, you have one input impedance here, ZE. Okay, so Z in is equal to the RE. Oops, equal to the RE parallel with ZE. Okay, so ZE here is equal to the since so ZE over here is equal to the VE over IE. Okay, in this case, so ZE is according to this node. Okay, from this node to the ground. Okay, from this node to the ground. So what are the voltage involved? It is actually VE. In this case, it is equal to the V pi. Okay, and IE is equal to the IB beta plus 1. Okay, let's take a look here. So your ZE, okay, your ZE, where should I, okay lah. Okay, ZE is equal to this node, VE, okay, this node, VE, over IE. Okay, so this one, VE is equal to the negative V pi because you have negative here, negative V pi. Okay, how about IE? In this case, IE is in this direction. Okay, and also your IB is from the IB here from emitter from base to at this direction, right? This is your IB. Okay, from base to emitter. So IB is going up. Okay, therefore your IE is equal to the IB negative IB beta plus 1. Okay, so if you simplify this, okay, V pi equal to the R pi, then you will get this portion equal to R pi over beta plus 1. Okay, all right, so this one you will get equal to 10.87 ohm. Okay, so your Z in over here will be equal to the RE is 1K parallel with 10.87. So you will get your Z in about 10.76 ohm. Okay. Okay, same, different with the PNP just now. So this one you have negative, negative. Okay, so Z out. Okay, so let's take a look on the Z out. So for the Z out, it is equal to the approximately equal to the RC, which is equal to the 4.3K ohm. Okay, all right. Okay, and then so let's derive for the all right, okay. So let's derive for the AV. Okay, AV. Okay, so Z in, Z out done. Okay, now you can find on your own AVOC. I want to find AV. Okay, AV. Okay, AV. Okay, AV is equal to the V out over V in with RL. Okay, so V out is voltage across who? Across which resistor for this case? Guys?
RC.
Voltage V out with RL. So V out equal to voltage across
RL.
these two resistor parallel. Okay. Yeah, same goes to let me show you in the previous slide. Okay, so when I said V out over here, so this V out, it is actually all voltage across all these resistor, because all these resistor in parallel. That's why V out is current times total resistor in parallel here. Okay, total resistor parallel here, which is RE parallel with RL. Same goes to here. Okay, I want to find AV with RL. Okay, therefore it is equal to the voltage across these two resistor. You need to parallel RC and RL. Okay, are you all clear? Hello? Time.
Yes, teacher.
All right, okay. So in here, the resistor is RC parallel with RL. How about the current? How about the current? How about the current?
AGM V5.
Yes, negative GM V pi. Okay, opposite direction. Okay, V in. Let's take a look on the V in. So V in equals to what? You can
Negative
see.
V5.
Yes, correct. Negative V pi, like this. Okay, so cancel out all the negative, so you will get let me use this. Okay, GM RC parallel with RL. Okay, so you will get about, oh, I didn't calculate. What is the answer here? No, we already have the answer. So I just put 274. Okay, 274. Can you all calculate on your own later? Okay, because GM over here is the same value, therefore GM is same like example in the previous one, millisiemens. R pi is about, hello? Hello?
Yes,
Uh,
teacher.
yeah, sorry, because I think I lose connection. No, okay. So yeah, so this is the value. So GM is 91.1 milli. RC is RC just now is, what is RC? Yeah? RC 4.3K. Okay, parallel with RL is 10K. Okay, and this one you will get about 274. Okay, 274. All right, so for the AVS, everything, it is the same derivation as in this slide. Okay, for the AI and everything, I trust you, you do it yourself? Can, right? But the most important thing is we derive, we try all the example, okay, and especially how to draw the AC equivalent circuit, okay, from this circuit to this, okay, to this, at least you understand this, and the rest you can find on your own, okay, for the Z in, Z out, AV. Okay, so if I have time before I upload, okay, I will write for the AI as well. Okay, now I'm running out of time because I want to have break 5 minutes to continue on the new topics. Okay, is that okay? Hello?
Yes, teacher. Yes.
All right, okay, so we take 5 first before we proceed on the next topic. So I have upload on the e-learning, okay, if you can see this. So I upload on the e-learning this topic on the frequency response. Okay, we'll start a bit on this. Okay. All right, take 5.
Okay, Lita.
Okay.
Lita, can you
Yeah.
please share the QR code, please?
Yes, yes. Wait. All right. Can you see?
Yes, Lita, thank you.
All right.
Oh, but I can't see. Wait. Okay. Thank you. Wait.
Nashra, can you scan once again? The attendance? I hope you can scan for the second time.
Hello, doctor.